Hello everyone. Today we will start with S block elements. It's a chapter of class 11. So in this video we will be talking about the trends in the physical properties. See, you will have plenty of questions in inorganic chemistry like arrange them in the increasing order of the property indicated or give reason type of questions. So you're not going to learn for each and everything increases, decreases. So you need to remember them with some concept. So that concept we are going to discuss in this video. Okay, so let's begin with the basic. What are S block elements? S block elements are those in which the last electron, or you can even write differentiating electron. Last electron enters S orbital of ultimate shell. Ultimate shell means the last shell. When we are writing the configuration, the last electron in these elements will be entering into the S orbital of the ultimate shell. So if you are asked to write the configuration of the S block elements, you will write the configuration as NS122. This is the configuration of S block elements. Now we know that in S orbital, 2 electrons can be accommodated. So in this S block, there are 2 groups. There is group 1 and group 2. Group 1 elements are also called as alkali metals. And group 2 elements are called as alkaline earth metals. These are called as alkaline earth metals. Group 1 elements are called as alkali metals because they are so reactive and they react with air, with water, and they form oxides, they form hydroxides which are alkaline in nature. They form oxides and hydroxides which are alkaline, so they are called as alkali metals. Alkaline earth metals, they are also reacting with air and forming oxides and hydroxides which are found in the earth. So they are generally termed as alkaline earth metals. Okay. Now, what elements can be included? Suppose we are writing the elements in group 1. The elements would be lithium, then you have sodium, potassium, rubidium, cesium, francium. Francium is radioactive. Element. So you can write their configurations taking help of the noble gases. Okay, so what you have to do is you can just remember the noble gases in order, that is starting from helium, neon, argon, krypton, then you have xenon and radon. Okay, you know the alkali metals general configuration would be NS1. NS1 to 2 is for S block elements. If you have to write down only for alkali metal, it will be NS1. So when you write their configurations of alkali metals, first you write noble gases and then you can just start off with 2S1, 3S1, 4S1, 5S1, 6S1 and 7S1. So in the last shell, there will be S orbital in which there is only 1 electron. Likewise, in alkaline earth metal, that is group 2, the general configuration would be NS2. And if we write their configurations, beryllium, magnesium, calcium, strontium, barium, radium. Okay, so even for these, you will be writing the noble gases, helium, neon, argon, krypton, xenon and radon, and then after writing their configurations you will be just adding on that S2. Okay, starting from 2. Okay, that will be what? 2S2, you'll have 3S2, 4S2, 5S2, 6S2 and 7S2. This is about the configuration. Okay, now we'll move on to the trends in the physical properties. Now, the first physical property is the radii. Whenever we are talking about these properties, we will be talking about down the group. So first we are beginning with group 1 only. Group 2 we will take separately. We are only talking about group 1. Okay, atomic radii. So down the group what happens? The size the atomic radii would be increasing. It is increasing. Why it is increasing? Recently we have seen the configuration. In the configuration what we found, the number of the shells are increasing. You saw that? Just see here, second shell, third shell, fourth, fifth, sixth, seventh. So down the group, one shell is being added. When one shell is being added, the atomic radii would be increasing. And if you compare the size of the alkali metals across the period, then too you will find that the alkali metals in each period are largest in size. In each period they are the largest in size. I mean, they are quite large. Of course, you can have the noble gases also comparatively more bigger in size, but alkali metals will have large size because across the period the size decreases. Okay. In noble gases, what you find is van der Waals radii. The van der Waals radii is large. So if you see in across the period, the largest would be the noble gases. After noble gases would be alkali metals, and then across the period it will decrease. That means the halogens would be least. Maximum will be the noble gases, then alkali metals, and then it will decrease. That is across the period. And down the group it has to increase. Right? Now, let us talk about ionization enthalpy. Now, ionization enthalpy is the minimum energy that I think you know that. Minimum energy required to remove electron. To remove electron from valence shell of neutral gaseous atom. Each term is important. It has to be neutral, it has to be gaseous, or it can be isolated gaseous atom. Either way it is fine. Okay, so because we said the size is large, because we said the atomic radii is big, their ionization enthalpy would be less. Because if the size is big, the electron would be away from the nucleus, so hold of the nucleus over the last electron will be less. All that details now you can just see in periodic classification. For that, all the videos I've already posted there. Okay, so ionization enthalpy is comparatively less if you compare with all the other elements in the period, and down the group ionization enthalpy decreases. It decreases because down the group the size is increasing. That is about first ionization enthalpy. Now suppose if I talk about the second ionization enthalpy. After second ionization enthalpy, all the elements will acquire the noble gas configuration. Right, because the configurations we have seen, they are all having only one electron in the s orbital. So that also goes means they will acquire noble gas. So their second ionization enthalpies would be very, very high. They will not be easily losing the electrons. Okay. Now the next property is hydration enthalpy. Now what is hydration enthalpy? Hydration enthalpy means the ion, whatever ion you have, positive or negative, or even it can be negative. So if they are surrounded by water, so if it is positive ion, the negative part will be towards the positive, the cation part. Right? If it is negative ion, then the positive part will be, that is hydrogen, will be toward. This process is hydration, in which the ion, that is cation or anion, is surrounded by water. That is called as hydration, and in that process hydration enthalpy is released. So hydration enthalpy is always negative. Hydration enthalpy is always negative. So if you talk about only alkali metals, their hydration enthalpy will be less. But if you are seeing down the group, size of the atom is increasing. So hydration enthalpy would decrease. Yeah, one thing you have to remember in this is that the hydration enthalpy is inversely proportional to size. It is inversely proportional to size. That means smaller the size, more will be the degree of hydration. So if we are asked to arrange these elements in the decreasing order of their hydration enthalpy, you will write down lithium ion, sodium ion, then you have potassium ion, then rubidium and cesium. So lithium ion is heavily hydrated. Okay, because of the smallest size of lithium ion, it has the maximum degree of hydration. It is because of this only you will find lithium salts. For example, LiCl, it is associated with two water molecules. Lithium carbonate, Li2CO3, this is also associated with water molecule. But otherwise you will not find any alkali metal which is forming hydrated salt. They do not form hydrated salts. Only lithium. So this is a similarity of lithium with the alkaline earth metals. Okay. Next property is oxidation state. Oxidation state of all alkali metals is +1. +1 because they can lose one electron readily and can form M+, which is quite stable. The nearest noble gas configuration, this configuration would be NS2 NP6 configuration. So that means they are normally existing in unipositive ion state, right? Then metallic character. Metals are those which can lose electron readily. So they are all metals because they have one electron only in the valence shell. So we can say that they are soft because they are very large in size. They are malleable and ductile solids. They are very, very soft. They are so soft they can be cut with the knife. And you can just see that, suppose sodium you are taking and you are cutting with a knife. When you cut with a knife, it will shine. It will have a luster. When you cut with knife, it will have luster. That is because the free electrons are there, and due to the oscillations of the electrons, the luster is visible. And you leave it in open for some time, that luster will fade away because it is going to react with the oxygen or water, moisture in the surrounding, and it will form oxide and hydroxide. Metallic character can also be termed as electropositive character. So we can say metallic character down the group is increasing. Down the group, metallic character is increasing because metallic character is related to ionization enthalpy. Lower the ionization enthalpy, more will be the metallic nature. So out of all, which is most metallic element would be the last one, that is cesium. Okay, the first one is not that metallic. Now moving on to the next property, melting boiling point. If we talk about alkali metals, their melting point, boiling point is very low because they are bigger in size, and melting point, boiling point for the metals depends upon the metallic bond. It depends upon metallic bond, and metallic bond strength is inversely proportional to size, because if the size of the atom is small, then the bond strength will be strong. If it is big, the bond length will be more and the bond will break faster. So you find that down the group, the melting point, boiling point will be decreasing. Okay, down the group, the melting point, boiling point will be decreasing. It will be decreasing. Why? Because size is increasing, bond length is increasing, the bond will break faster, so the melting point, boiling point will be decreasing down the group. Right? Density. Now if we have to say about the density, we will say that the density of the alkali metals would be comparatively less. It will be quite low. Why? Because they are larger in size. You know, density is mass upon volume. There are two factors which are mainly talking about the density, which can contribute to what the density would be. And you know that from lithium to cesium, that is down the group, mass is increasing, volume is also increasing. So when both are increasing, then what will be the deciding factor? Whichever increases more. So it is found that down the group, increase in mass is much more than the increase in volume. So it is found that down the group, density increases. But there is one exceptional case, that is if you check the elements, sodium, potassium, lithium, sodium, potassium, rubidium. So potassium should be more than sodium, but it is less. Potassium is less than sodium. This is a reason question that is asked. Why is potassium lesser than sodium? The density of potassium is lesser than sodium. That is because of abnormal increase in the size. Potassium has the abnormal increase in the size. This increases to such an extent that the volume is more. Volume is more means the density would be less. So this reason question can be asked. Potassium density is lesser than sodium, though it is placed below it because abrupt increase in the size. You can just check the configuration wise. There are vacant d orbitals which causes the increase in the volume. Due to much increase in the volume, the density is comparatively lesser. Right. The next property is flame coloration. Now, one very important property of the alkali, in fact S block elements, but since we are only talking about group 1 as of now, so we will say that they all impart color to the flame. They impart color to the flame. Now, why do they impart color and how we perform that? I'll explain. What you do is you take a watch glass. In the watch glass, you take salt. To the salt, you add 1 or 2 drops of concentrated HCl to make a paste of it. The purpose of adding concentrated HCl is to convert this into volatile chlorides. We are converting them into volatile chlorides. So this paste is taken on the platinum wire. Platinum wire is something like this. There is a loop over here and there is a holder. On this loop, we just take the salt and put it onto the flame, on the burner. We will keep it on the burner and the flame coloration would be seen. Okay, so they all impart color to the flame. Reason for why they impart color to the flame is they are larger in size. So when we just expose it to the flame, the electrons get excited. They go to the higher level and they cannot remain there in the higher level because they would be unstable. So they come back to the original. So when they come back, they will emit out the energy with which they have gone up. So they impart color. And due to different size, different amount of energy is required for excitation of the electron. So they exhibit different colors. Like lithium. Lithium shows crimson red color, bright red color it shows. Sodium, it is showing golden yellow. It shows golden yellow color. It imparts golden yellow color to the flame. Potassium exhibits violet color. Okay, rubidium shows red violet color to the flame. And cesium imparts blue color to the flame. They all impart color to the flame. So when we perform salt analysis in the lab, in practicals, we will be able to identify if it is any S block element present by the flame coloration they impart. The last property about S block elements will discuss that they exhibit photoelectric effect. Okay, they exhibit photoelectric effect. Now, what is photoelectric effect? It is the phenomena of ejection of the electrons when the light, that is electromagnetic radiations, fall on the surface of the metal. Suppose you have the surface of the metal, light of certain minimum frequency, when it falls, they will emit electrons. So because their ionization energy is less, they have the tendency to show this effect, or that is photoelectric effect. And in this the complete alkali metals, you have two elements, potassium and cesium. They are being very commonly used in photoelectric cell. They are very commonly used to to exhibit this photoelectric effect. That is why they are commonly used in the solar cells. I hope it is clear whatever we have discussed, the trends in the physical properties today. Okay, so see you in the next video.